Okay, now, before we start, do you have any questions about the things that we have been doing? Now, just to refresh, we first started the effects of the magnetic field. We have seen that it exerts forces on moving charges and hence on current carrying wires. That was what we had first started studying the magnetic field. And on Tuesday, we started to discuss what happened, how the magnetic field gets created. And we have seen that if you have a current carrying wire, it doesn't only feel force in the presence of the magnetic field, it also feels a force due to this, creates this magnetic field. So any questions on these? That is not a magnetic force. Okay, other questions? Okay, so now this was what we had been discussing. If we have a straight wire and if it carries a current, we said that it creates a magnetic field whose magnitude at a given point was mu0 over 2 pi I over d. This is the magnitude. D is the distance from the wire. And mu0 was this permeability, and we had defined it as 4 pi 10 to the power minus 7 Tesla meters per ampere. And this was our constant. And the direction, we determined it using the right-hand rule. So we just wrapped our fingers around the current such that our thumb points in the direction of the current. In that case, the other 4 fingers just show the direction of the magnetic field around this wire. And we also said that the magnetic field, if we show them as a magnetic field lines, they just form circles around the wire. This is the direction of the magnetic field lines in this case. Now, let's look at a property. If you look at this one, does this, I mean, if you remember electrostatics, this looks like something in electrostatics. Do you remember what it looks like? The potential? Okay, it looks like the potential, something else. I mean, something else that depended on the distance as 1 over the distance. Besides the potential, the electric field, in which case, no, the electric field in one particular example, it had exactly this behavior. If we had an infinitely long wire that's carrying a uniform charge, the electric field created by this wire had exactly the same behavior. It exactly had this one. Now, in electrostatics, we had the Gauss's law. And which, okay, from the Gauss's law, we could drive the analog in electrostatics. Now, what do you think would be the similar Gauss law in magnetic fields? Okay, 1, 0. Why? Okay, the magnetic field lines are always closed. So if you take a closed surface, they always enter the surface and leave the surface. Magnetic field lines cannot start inside the surface, cannot end inside the surface. They don't have ending points. So this would be 0. Okay, so this wouldn't be useful to determine this kind of a law. But let's look at this one. Suppose we have this current just getting out of this screen. Let's imagine a circle this time. Of radius, let's say r. Now, what is the magnitude of the magnetic field along this circle? I over d. This is the form I over r. Now, what is the circumference of this circle? circumference, çevresi, 2 pi r. This is equal to mu0 times I. Well, let's see. What is the direction of the magnetic field? Counterclockwise or clockwise? Others? Counterclockwise or clockwise? It's counterclockwise. This is the direction of the magnetic field. Let's just imagine we take this path and we divide it into small pieces of each length dl. So if you would calculate b dot dl along this circle, it is equal to mu0 I. Now, ninth thing, it is independent of the radius, so if we take a small circle or a large circle, this integral is always the same. Now, in fact, it is even independent of whether you take a circle or some arbitrary shape. So this is what we call the Faraday's law. No, I didn't say b dl equal to 0. This is b dot ds equal to 0. This is an integral over a closed surface. Now, this is integral over a closed surface. And here we have an integral over a closed line. Closed loop. So this is a line integral. We are going over a line which is closed. In the previous case, well, although we use the same symbol, this is over a closed surface. We are summing over the closed surface. Now, how do you distinguish the two? Usually, you use either S or A to denote the area. So this is an area, an integral over an area that is closed. And you usually use L or R to show line, pieces of line. So this is a line integral which is closed. Which one? This one. So in electrostatics, we already said that this E dot ds just counts the, in a sense, counts the number of field lines. It counts the flux that leave a given surface, that goes from inside to outside. But here, if you look at here, the magnetic field lines are closed. If they enter a closed region, a closed surface, they also leave the same surface. So the net number of field lines leaving a given surface will be 0. This is also the statement that there are no magnetic charges. If you look at electric field, we have electric charges. Electric field lines start from the charges and they end on charges. But in the magnetic field, we always have dipoles, like the magnets. The magnets have a north pole and a south pole. If you cut it into two, it still has a north pole and a south pole. They always come as a dipole. You never have a point magnetic charge. So this is that statement. This would give us the magnetic charge enclosed in this closed surface, which is 0. There is no magnetic charges. Where? In this? If it was 0, what would happen? U0 times I would be 0? Or? Now let's say if B is 0, mu0 times I should be 0. Now, like the electric field. Yeah. If electric field is 0, there are no charges around. Now, this is just a plausibility argument. It says that at least for circles, this integral is independent of the size of the circle, but we can even prove that this integral is independent of the shape of the circle. So we have this current I. Let's just imagine an arbitrary shape going around it. This is an arbitrary shape. We already know that if we have a circle like this, B dot dl around that surface is nothing but mu0 times I. Now let's take a very small segment of both of them, and let's choose them such that they see the same angle. Now here we have let's say dl1. Here we have dl2. Here the magnetic field is in this direction, B1. Here the magnetic field is in this direction, B2. Let's say that this distance is R1, this other distance is R2. Now B1 is mu0 over 2 pi R1 over, no, I over R1. B2 is equal to mu0 over 2 pi I over R2. I just imagine two curves. One is closed curve, an arbitrary shape. The other one is a circle. Now, I will just show that the contribution from this segment and the contribution from that segment are equal, as long as they see the same angle over here. That's what I'm planning to prove. Once I prove that for all segments on this arbitrary shaped loop, there is a corresponding segment on the circle which gives the same contribution, and I already know the result for the circle. Now, B1 dot dl1 is equal to B1 times dl1 parallel, or let's say perpendicular. Just imagine this is where the current is. This is the distance, the L1, R1. Okay, this is the L1. This is the direction of the L1. My B1 is in this direction. If I take the scalar product of this vector and this vector, I can write this scalar product as the magnitude of this vector times the projection of this one in the same direction. That is what I'm calling dl1 perpendicular. It is perpendicular to this radius vector. Which is equal to mu0 over 2 pi I1 dl1 perpendicular over R1. Now I can do the same thing for B2. That dl2 will be equal to mu0 over 2 pi. No, this is not I times dl2 perpendicular over R2. Now let me just exaggerate it a bit. So I have, this is where is my current. This is where is dl1. It is this vector. This is where I have dl2. And this is dl1, dl2 perpendicular. And this is the angle theta. Okay, this is R1, the whole thing is R2. Now, how had we defined the angle theta? It is the arc length divided by the radius. So it is equal to dl1 perpendicular divided by R1, which is the same thing as dl2 perpendicular divided by R2. They define the same angle in radians. So that kind of completes my proof. So if you come back here B1 times dl1 is equal to some constant times dl1 perpendicular over R1, and B2 dot dl2 is nothing but the same constant times dl2 perpendicular over R2. But these two things are equal. dl1 perpendicular over R1 is equal to dl2 perpendicular over R2. They are nothing but the angle over here, and they see the same angle. So that completes my proof that B1 dot dl1 is equal to B2 dot dl2. In fact, this just proves that if you have any circle, any loop around your current, whatever the shape, any two loops around this that covers this current, this integral B dot dl is the same for all of them. That is what we had proven. For the circle, we know that it is mu0 times I. So for any circle that goes around our current, it's mu0 times I. Around any closed loop is mu0 times I. Okay, there are a few things that we have to pay attention to. One is, for example, if we change the direction of the current, B should change. If the direction of the current changes, the direction of B changes. If the direction of B changes, this integral should change its sign. If it is positive for one current, when we reverse that current, this integral should be minus. That means we have to assign a sign to this current. This current over here is not just a positive number. It can be positive or negative depending on how the current moves. Now, the positive sense of this current we choose as the to determine the positive sense, again, we use the right-hand rule. So if you choose any closed loop, just wrap your fingers around the loop. So the direction of your thumb points the positive direction of the current. So if this is my loop, this is I1, let's put another current over here, I2, B dot dl for this configuration. What is B dot dl for this configuration? Well, just wrap your right hand around your loop. Your thumb is pointing out of the screen. So I1 is a negative current, I2 is a positive current. So this is equal to mu0 times I2 minus I1. It's the same. It's similar to the Gauss law. Still, the currents can be positive or negative, depending on their directions. In the Gauss law, we had the charges that could be positive or negative. Now, let's do a few more examples. So let's say that we have a current that is running in this direction, which is I. Let's imagine another current which is running in this direction, which is also I. Now let's imagine several loops. For example, let's take one that goes like this. This is loop 1. So B dot dl around this loop 1. This is equal to okay, loop 1, let's give it a direction also. This is the positive direction. Now both of them, I mean the loop is closer to you from both of the wires in the front, and it's going around both of the wires. So if these are your loops, your wires, the loop goes like this. Does it depend on that angle? Is it magnetic field in this case is not zero. Both of the wires create a magnetic field. Nevertheless, according to the Faraday's law, this is equal to mu zero, I minus I. This is equal to zero. Now, why I minus I? Now, if you just, okay, this is the, okay, this is the, like our currents. One current is going down. This is the positive direction of the current. Let's say the other one is going upward. And this is our ring. So if you just wrap your fingers around the ring, the current that is going in the upward direction, not necessarily vertically upward. Upward just means that it's going below the loop to above the loop. So if it is going upward, it contributes a positive to our integral. If it is going downward, we call it a negative current. So this one is a positive current. It's going from below the ring to above the ring. This brings a positive contribution, whereas this one brings a negative contribution because it's going from above the ring to below the ring. So that's why one of them comes with a positive sign, the other one comes with a negative sign. And that is why the integral is zero. The magnetic field, I repeat, is not zero. But nevertheless, the integral is zero. Just like think of in terms of the Gauss law. In the Gauss law also, if we had, for example, one positive charge, one negative charge inside our Gauss law, the integral of the electric field was zero over the surface. Although we know that the dipole, this dipole configuration creates a non-zero electric field. It's the same thing over here. Now that is infinite. These wires are still infinite. No. But let's take some other loops. This was one loop. Let's imagine a second loop like this. Again, the same wires. Plus or minus. Is equal to mu zero times I. Now, okay, let's again construct our, okay, these are our wires. They are creating a magnetic field. Now my loop is just going around this one of them only. So this is the positive direction of the wire, of the current. And the current is running in the positive direction. Now this doesn't mean that the magnetic field around this loop is created only by this current. The magnetic field at every point on this wire is created by, receives contribution from both this current and the other current. But nevertheless, when you take this integral, the contribution to the magnetic field from this wire, they just give zero. Whereas from this wire, they sum up to give mu zero times I. Okay, let's take the third loop. So these are my current carrying wires. I take a loop somewhere over here, this loop. Zero, non-zero. Now it will be zero. The magnetic field is not zero. Nevertheless, this integral is zero. Is this clear? Okay, let's do another example. Let's just imagine we have an infinite plate. And this plate has a uniform surface charge density sigma. And let's assume that this whole thing is moving with some speed v. We have to find out what's the direction of the magnetic field, what's its magnitude, etc. We have to find all of it. We are not interested in the electric field. We only want to find the magnetic field. I have these charges. They are moving. They are moving. So I have moving charges, which means I have a current there. If I have a current, that means I have a magnetic field. It's infinite. Well, let's say that it is, well, even if it is infinite, its motion will have a significance because I have moving charges. If I fix one charge, if I follow it, it will be moving. Now, your friend has an interesting comment, because if it is infinite, you will not see any changes as it's moving. So how can you tell that it is moving or not? But if you can just mark any one of the charges, and you will see that it is moving. So that is what will be creating the magnetic field. But you see, I'm not interested in the force due to the magnetic field. I would like to find the magnetic field itself. And this one, well, okay, that is one answer. It will be a circular. Well, let's see. Now, I have all these currents moving. Let's just imagine, I only know the magnetic field of a single wire, right? But I can divide this infinite plate as many single wires. So I will just write this thing. I can sketch it as very small strips. Each one of them are moving. So each one is carrying some current. For the time being, I'm not interested in the amount of current that they carry, but they will be carrying some current. First, let's determine the direction of the magnetic field. That's what I'm first aiming at. Now, let me just draw it from another angle. So here, this is my infinite plate. I'm moving it like this. So let me just assume that I'm looking at it just like this. It's moving towards me. So there are currents coming just right towards me in my direction. There is one current over here, another one. There's an infinite plate. Let me just choose this point. What will be the direction of the magnetic field created by this wire? So it's a wire that's moving in this direction. It's a straight wire. To find the direction of the magnetic field, I just wrap my hand around the wire such that my thumb points the direction of the current flow. So at that point, the magnetic field created will be in this direction, B1. And this is 90 degrees. Well, let me choose another one. Okay, this is the direction of the magnetic field created by the wire over here. Now, it is infinite. I can just take another one right on the other side. Just this one. What will be the direction of the magnetic field that will create? Left a bit upwards. Again, just use the right-hand rule, wrap your finger around that very small segment of the plane, and then your fingers will just show you the direction of the magnetic field. So it will be something like this. Let's say this is B1, this is B2. And let's assume that I'm just dividing this infinite plate into very thin filaments of equal thickness. So they will be carrying the same current, each one of them. So the currents are equal, the distances are equal. What can you say about the magnitude of the magnetic field? Well, okay. Are they equal? One is larger, other one is smaller. They will be equal. Remember, the magnetic field of an infinitely long wire depends on, this is constant, on the current and the distance from the wire. These two wires, these two very small segments, this one over here and this one over here, they carry the same current, and they are at the same distance from my point P. So furthermore, if you consider this horizontal plane, this horizontal line, you see this angle and this angle, they are equal because I'm just taking symmetrical points. But that means if this is my B2, this is my B1, this angle is equal to this angle. But that also means B1 plus B2 is horizontal. Okay, I used symmetry of my plane to argue that every such piece of current running on this part has a symmetrical current on the opposite side. And both of them create, the sum of the magnetic fields that both of them create will be horizontal. So I don't know the magnetic field yet, but what I know is that the magnetic field will be horizontal. Since for every contribution from this side, there is a symmetrical contribution from the other side, the sum cancels the vertical component. That we know. It's not circles, they are horizontal, parallel to the plate. What about on the bottom side? On this point, what can you say about the magnitude of the magnetic field? The direction of the magnetic field, sorry. Horizontal. Well, at the point P, the magnetic field is horizontal towards the left. At the point P prime, well, it will be horizontal, but is it towards the left or towards the right? It will be towards the right. You see, if you wrap your fingers around the wire, this segment will create a magnetic field in this direction. This segment will create a magnetic field in this direction. Oh, sorry. Okay, these are different figures. Do you agree on the directions? So this is my infinite plane. It is moving towards me. So it's just this plate, infinite plate, is just moving like this at a constant speed. Now let's see. Let us choose a Faraday loop. Okay, what I know that it is horizontal in the top and the bottom. Well, the top and the bottom, they are quite symmetrical. So the magnitude should be the same, in the sense that the magnitude at this distance, t, should be equal to the magnitude at this distance, t. So the magnetic field above, let me just choose a direction. This is my x direction, let's say. Above the plane, magnetic field has some magnitude. It might depend on d, I don't know yet. It cannot depend on anything else. And it is in the x direction. Sorry? No, this is your current. Yes. The plane is moving towards you. So this is the direction of V. Okay. Let me put a minus sign over here. And the magnetic field below should be B times D, again in the x direction. They should have the same magnitude, because up and down, they look the same. They are the same. It's just the direction that changes. If you go back to the previous case, if you take P and P prime to be at the same distance from the plane, the magnetic fields created by these two small currents, they will have the same magnitude. The resultant vector will have the same magnitude. If I choose a distance that is smaller, a point that is closer to the sheet, the magnitude might differ, but as long as they are at the same distance on both sides, they will have the same magnitude. That is why I put the same magnitudes in both cases. I only know that the directions are different. So that is why I have a minus sign over here. At this part, this B of D, I'm expecting it to be positive, because we already said that the magnetic field above the plate is in this towards the left, the magnetic field below the plate is towards the right. Now let's choose our Faraday loop. Let's just choose such a loop. Now the magnetic field above, I know that they are like this. Below they are in this direction. So let's calculate B dot dl over this loop. This is equal to A, B, C, and D. Let's just assume such a shape, such a direction for my magnetic field, for my loop. Or let's say, let's choose this direction for my loop. I'm going around my loop. This will be, okay, the contribution from A to D plus the contribution from D to C, from C to B, and then from B to A. I just divided my loop into smaller part pieces, and my loop integral is nothing but the sum of all of them. Questions? Well, let's see. Now, at this level, I don't worry about the current now. I first determined some general property of the magnetic field. I know its direction now. I know on which parameters it depends on. It depends on the distance from the plane, but it doesn't depend exactly on where I am. I mean, if I'm at this distance, the magnetic field here and here and here and here, they will all have the same magnitude as long as my distance doesn't change. Those are the things that I have determined. And using those information, I have chosen a path such that it is either, as I go around the path, I am either staying at the same distance from B to A and from D to C, my distance from the plate is the same. And as I go from A to D or C to B, I'm moving perpendicular to the magnetic field. But since as I'm moving from A to D and C to B in this integral and this integral, my dLs are always perpendicular to B. B dot dl is 0. So there's no contribution from these two. Now, as I'm moving from, let's say, D to C, from D to C, my dl is equal to, well, let's do another way. As I'm moving from D to C, B is just a constant. Since B is constant, I can just take it out of my integral, and this B is given by this constant, minus B as a function of t in the x-hat direction, time from D to C of dl. Plus, as I'm going from B to A, again the magnetic field is just constant. It's given by this expression, from B to A of dl. These are just constants, so I just took them out of the integral. Now, this integral is nothing but the difference of RC minus RD. Well, let's just assume that this length is L. In that case, RC minus RD vector is nothing but a vector connecting point D to point C, but that is nothing but L x hat. Now, if I look at the other one, this integral over here is RA minus RB, but this is nothing but a vector connecting my point B to point A, but that is minus Lx hat. Well, I can just do the scalar products. X hat dot x hat is 0, is 1. X hat dot x hat is again 1. So this will be equal to minus 2L B of t. Okay, this is our integral of the magnetic field. Now we have to relate it to the current. Now, any questions on this one? Well, let's look at those integrals. I'm going around this path. This is my path. I have to specify it. And then I'm saying that, okay, in this part, I'm moving from the point A to point D. I'm moving from this corner to that corner, along this path. The changes in my position, which I denote by dl, dl is pointing in this direction, in the vertical direction. But B is horizontal. Either it's pointing in the plus x direction or it's pointing in the minus x direction. But in both cases, it is vertical to my displacements. So I have two vectors that are perpendicular to each other, so their scalar product is 0. Other questions? Now this is my plane. This is the direction that they are moving, and I had chosen such a path. This is length L. Now, is the current positive or negative? Let's start with determine the sign. Okay, that is the direction of the current. So is it a positive direction or negative direction? Consider the loop that we are studying. Our loop is going in the clockwise sense. So if you just wrap your fingers around your loop, your thumb points into the screen. But the current is going out of the screen, so the current is negative. I enclosed, let's say. Now let me also draw another view of the same thing. This is the direction of the motion. And this is the length L. Now how can I determine the current? What was the definition of the current? What is the definition of the current? No, the definition of the current. Okay, we will relate it to sigma in this example, but the general definition of the current. It is Q over T. So delta Q over delta T. Delta Q is the total charge that passes through a given area in a time delta T. So let's just take the time delta T. In that time delta T, this is, let's say, V delta T, all the charge within this rectangle passes through my loop. Because after a time delta T, this line will have moved at this point. All the charge in between these two lines, it will just pass through my loop. Now, what is the area of this rectangle? L times V times delta T. This is the area. Now, the surface charge density, we said that it is sigma. Sigma is the charge per unit area. So this is the total area. So the total charge is sigma times this area. This is the total charge in this rectangle, but all of this charge passes through my loop in a time delta T. So the total enclosed charge, that is the total current that is passing through my loop, is LV times sigma. Now let's see, B dot dl. This is equal to, well, this should be equal to mu0 LV sigma. This is our Faraday's law. But we had already evaluated this integral. This is minus 2L B at D. This is equal to mu0 L V sigma. Okay, now L's cancel. And we are left with B of D is equal to minus mu0 over 2 V sigma. You see, this is not my loop. Don't confuse this rectangle with my loop. Here what I am saying is I'm just following, okay, this is my infinite plane. I'm just assuming a loop like this, a rectangle like this. And it is moving downwards. So all the current that passes this line passes through my loop. In a time delta T, this plane will move a distance V times delta T. So it will start from here. If you just imagine that this is the segment of my loop, all the current in this area, all the charges in this area will pass through my loop. Now that rectangle, okay, the plate has moved a distance V times delta T. That is why the height of this rectangle is V times delta T. So that gives me the total charge is LV delta T times sigma. So the total enclosed current is given by this expression over here. Okay, we can discuss it later on. I mean, this is infinite. You cannot even put it in a generator. Questions? Okay, see you after 10 minutes.